Are you grappling with a data science project and feeling stuck? You're not alone. Today, we're diving into a common challenge: how to effectively place desalination plants along the California coast using k-means clustering. I totally get it. Working on a project that involves real-world applications can be overwhelming, especially when you're trying to optimize locations based on complex data. It's a tough nut to crack, but you're in the right place to find some clarity. Let's break down the specific question at hand. One user is trying to determine the best locations for K desalination plants to minimize the distance to various zip codes. They have data on zip codes, cities, counties, populations, latitude, longitude, and water amounts. But there's a catch. They need to keep the centroids constrained to the coast. Sound familiar? Let's explore this together. So why is this a challenge? The standard k-means algorithm doesn't inherently restrict centroids to specific geographical areas. This can lead to centroids being placed inland, which is not ideal for a coastal project. Let's discuss some potential solutions. And stick around. By the end of this video, you'll have a solid strategy for implementing k-means with a coastal constraint, plus a bonus tip that could save you time in your project. To begin solving the user's problem, we need to modify the k-means algorithm to ensure that the centroids remain on the coast. The first step is to identify the coastal zip codes from the dataset. Next, the user should implement a modified k-means algorithm. This involves running the standard k-means clustering, but adding a constraint to adjust the centroids after each iteration. After adjusting the centroids, the user should check the distance of each centroid to ensure they are still minimizing the distance to the coastal zip codes. This step is crucial for validating the clustering. Finally, the user can visualize the results. Plotting coastal zip codes and the final centroid locations will help in understanding the effectiveness of the clustering. Fun fact: did you know that the concept of k-means clustering dates back to the 1950s? It's amazing how this technique has stood the test of time and is still relevant in solving modern problems. Now let's look at the answers provided by other users. An alternative approach suggested by a user involves defining possible centroid locations along the coastline. Instead of calculating the mean of the clusters, the algorithm would select the nearest point from this predefined set of coastal points. This method simplifies the problem by focusing on two dimensions, latitude and longitude. The user provides a code example that demonstrates this method. It includes functions to generate possible points, cluster data, and reevaluate the centers based on proximity to the coastal points. The goal is to minimize the total distance to these points. That's the end of that answer. Let's see another perspective. This user points out that k-means does not minimize distances, but rather minimizes squared errors, which can lead to significant differences in results. They provide an example showing that k-means can yield a centroid that is much worse than the optimal location. They emphasize that k-means is sensitive to outliers and suggest using Haversine distance for geographical data. Additionally, they recommend treating the problem as a generic optimization challenge instead of relying solely on k-means. Here's a pro tip. When working with geographical data, always visualize your clusters on a map. This can provide insights that numbers alone might not reveal, helping you make better decisions. And there you have it. With these strategies, you're well on your way to successfully placing desalination plants along the California coast. If you found this video helpful, don't forget to subscribe for more data science tips and tricks. Happy clustering!